already posted part 1 on Canvas, so you can go watch it through again, or go look at specific problems as you are kind of going back through the review. But today, we'll start at number 13 and see if we can get through the rest of this. Okay, so we're in chapter 3 at this point, where we're talking about exponential functions. So the next one is asking how much would you need to invest if you want to have, or at a certain percentage, at a certain rate, if you want to have $10,000 after, I think in my case, it's after 5 years. So what is that 10,000? What is that 10,000 going to represent?
You said you were looking at 10,000 after that number?
Yeah, right.
It's the future value.
Future value, very nice. So that 10,000 represents my future value, and what am I solving for?
The present value.
Present value. So what I'll go ahead and do is I'll go ahead and label that as just P, and that means we're solving for P naught, right? That initial value that you're going to need to find, okay? That means, but it also gives me the rate. In my case, it's 4.6%. And then it also gives me time, right? In my case, it's 5 years. So if you remember, there's 2 different ways I can set this up. First of all, I can just set this up using my basic exponential equation. But where is that 10,000 going to go? Right? My basic equation is just this for continuous exponential growth. Where does that 10,000 go? On the other side of the equal sign, right? So I'm going to have that 10,000 just over here. And then we're solving for P naught. We're solving for that initial value. And so I guess I'll just replace these up here. My rate is 0.046 and my time is 5. So that's one way I could do it, but what's the other way I could do it? There's an alternate way that I could actually work through this problem. I can solve directly for present value by doing what?
I don't remember. Do you make the rate negative?
Exactly. I can just make the rate negative. I can change it into an exponential decay function. Very nice. What do I put as my initial value? The 10,000. Because it's kind of like you're working backwards. I'm ending with 10,000, and then I'm working backwards to see what I'm starting with. So that 10,000 becomes my starting point, and then you just make the rate negative. So negative 0.046 times 5. So you can use an exponential decay function in order to model present value. Very nice. And so that's something you can just throw into your calculator. And so I think in my case, I get 7,945.34. Okay. Very nice. And that's rounded. Ooh, goodness. Okay, any questions on that one? So that's just a good present value, future value type problem that we can think about. Okay, next one. Move on to 14. Okay, 14 is all about an office machine depreciating in value. And what's different about this one is it's not given to us as a continuous exponential function. My base is not E. In this case, I have a base of 0.79. Okay. So this question's all about how do we work with functions that don't have base E. Okay. So part A, this one has multiple parts. Part A is just asking, hey, what's the derivative? What's the derivative? Well, what do I do with this 9,200? What am I going to do with that? Keep it there, right? Constant multiple property of derivatives, right? So I'm just going to keep that 9200 there. And then I can just focus on just that piece, that exponential piece. So this goes back to, hey, what's my derivative formula? If I have an exponential function, this is still exponential because your variable's in the exponent. What's my derivative formula if I have an exponential function that's not base e? I think this one will be on your formula sheet. But what do I do? Do I subtract one from the exponent? Do I subtract one from the exponent? No, that's power rule. So I don't want to use power rule on this because it's still an exponential function. So what was the rule for e to the x or e to the t? What's the derivative of e to the x? It just stays the exact same. And the same thing is true here. It's going to stay the exact same. Oh, got to go back to my regular pen. It's going to stay the exact same. There's just one extra thing that I have to do. I need to multiply by...
The derivative of the inside.
Well, this isn't necessarily chain rule because I don't really have an inside function, right? I don't really have an inside function. So it's not that I'm using chain rule. This is just my rule for an exponential function that doesn't have base e with base a. Right here, and we can review it over here. If I have a to the x and I want to find the derivative.
Multiply it by a natural log.
Yeah, that's exactly right. You keep it the same and then multiply it by natural log of whatever the base is. So natural log of a. So in our case, I've already kept the 0.79 raised to the t power. I'm going to multiply it by natural log of 0.79. Very nice. And there's my derivative. Okay. Very nice, very nice, very nice. What does this represent? What does v prime of t represent? Right, I'll write it out. What does v prime of t represent? So in order to understand this, first we have to understand what does my original function represent? What does this function tell me? What does that function tell me?
Value after t time.
Yeah, we're using v for value. It's the value of this office machine. And notice it's a decay function. So what's happening to the value?
Depreciate.
It's depreciating. It's going down. So this is the value of the office machine after a certain amount of time. What does the derivative tell you?
The amount lost per year.
Right. What is a derivative? It's a rate of change. So it's telling you how that value is changing each year. Exactly. So it gives, let's see, it represents the rate of change in value of the machine per year. And the way Mona described it is a great way to think about it. How much value does it lose each year? And we know it's losing value because it's a decay function. How much value does it lose each year? I like it. Very nice. Okay, any questions about this one? Another good little exponential function. Okay. Now we get to chapter 4. Okay. So chapter 4 gives us a velocity function of a particle. sorry, number 15. Number 15 gives me a velocity function for a particle. Okay. And then part A asks me, okay, let's see, let me make sure I get the wording right here. What number is this one, 15? Yeah, oh, wait. Oh, I skipped one, didn't I? I skipped one. Scratch that. I forgot I added one to the review. So, 15 is just this integral of -2 over the 6th root of x to the 5th. So chapter 4, right? Chapter 4, we started talking about integration. So here I have this indefinite integral. What is it really asking for if it's just an indefinite integral? What am I going to try and find here? The antiderivative. So that's all this is really asking for. Is just what's the antiderivative? But man, that's an ugly function. So, okay, I can move the denominator to the top using what? How do I do that? How do I move it to the top like that?
Would be x to the 5th to the negative 1.
Right, I have to use like a negative exponent to help me out with that. Okay, so I know I can use negative exponents to move it to the numerator. Okay. But what about the 6th root of x to the 5th? Yeah, I can rewrite that as just one single exponent where the denominator of the fraction, where I can write that as a fraction exponent, where the denominator of that fraction is whatever the root is. And then the numerator of the fraction is whatever my normal power is. So, right, the root was my denominator, and then the power was my numerator. And then, like we said, because it went from the denominator to the numerator, I also have to make that a negative. Very nice. Yeah, can't forget that. Okay, very nice. So now that we've rewritten it like this, what type of function is this? Just a power function. Right. This is a power function, so I can just use my power rule on it. So,
Take the -2 outside of the...
yep, I can rewrite it with the -2 outside the antiderivative, so I don't or outside the integral, so I don't have to worry about the -2. I can just focus on the x to the -5/6. Okay. And then my power rule for antiderivatives, what do I do to that exponent?
1 over...
Yeah, I will divide. And I'm going to divide by whatever the new exponent is. So what's the new exponent going to be? 1/6, because I'm going to add 1. -5/6 plus 1 or plus 1 gives me 1/6, and that means I'm going to divide by 1/6. Very nice. What am I missing? Plus c. This is an indefinite integral, meaning I'm just finding the antiderivative, and the antiderivative can have any constant added on to it. Okay? Flip that 1/6 around, and you get -12x to the 1/6. Or -12 times the 6th root of x. Very nice. Awesome. Any questions about this one? Okay. Very nice. Okay, now we get to that particle one. Okay, so we have a particle that's being released as part of an experiment, and its velocity can be modeled by that equation. And we're measuring this in meters per second, so V is meters per second. And part A is, how far does it travel in the first, the first 6 seconds? How far does it travel in the first 6 seconds? So why is this antiderivatives? Why does this fall under chapter 4, which was all about antiderivatives and integration? Yeah,
I'm
Mona.
just asking about things like velocity and acceleration.
True. But this question specifically in part A is asking about that's position, right? Yeah, how far is traveled is talking about position, but it only gives me the velocity function, which is the derivative position. So I have to go backwards, right? And going backwards requires antiderivatives, integration. Now, what's nice here, though, is if it gives us a specific time period, then how can I set this up?
You plug in 6 seconds per time.
Ooh, I plug it in where?
Excuse me.
Where do I plug in 6 seconds?
Usually you would do it for t because it's 6
Right.
seconds.
Into my velocity equation?
Into your antiderivative.
Into my antiderivative. And so because that's I'm going to be plugging these values into the antiderivative, I can actually just write this as a definite integral. Because when I take when I find my integral, I'm finding the antiderivative, and since I'm going to be plugging in that 6, I can put that as one of my bounds. Which bound?
Upper bound.
The upper bound. What's my lower bound?
0.
0, because it's the first 6 seconds. So it's from the time that I start to the time, or to 6 seconds. So everybody okay with that? I can write that as a definite integral. And that's something we talked about a little bit in class, where if you have a rate function, then your definite integral represents the total change over that specific interval. Cool. So, awesome. So then I can just find my antiderivative. My antiderivative is 0.2 t cubed plus 6t squared, evaluated from 0 to 6. Everybody okay with that? 0.6 becomes a 0.2. Oh, that's a negative 0.2. Yeah, negative 0.2. That 0.6 becomes a 0.2 because you divide it by 3. And then the 12 becomes a 6 because you divide it by 2. Plug in your values, and you're left with 172.8 minus, what happens when you plug in 0? You just get 0. Oh, goodness. So this means total, over those first 6 seconds, the particle moved 172.8 meters to the right, because it's positive. Okay. Part B asks, what about the next 6 seconds? How would this problem change in that case? If now I'm asking, okay, how far does it travel in the next 6 seconds?
From V7 to 12.
I'd actually start right at 6,
We're at 6.
because 6.1 is now in my new interval. We okay with that? Right? So start right at 6, and now I'm integrating from 6 to 12. It's the same reason that for the last one we didn't start at 1, we started at 0. So, everybody okay with that? Cool. And so what's nice about this one is the same antiderivative. It's just new numbers that you're plugging in. So I think in my case, we won't worry about it. You guys can do that on your own. Okay, any questions about this one? Okay. Once again, this one requires integration because it's asking me about distance, but giving me velocity, right? But giving me the velocity equation. So I can use integration to find that total change. Okay. And if you remember, that's really what that chapter 4 project was for you guys, right? Is you created a velocity function and then integrated that velocity function to figure out the total distance that you went. All right, 17. What are we on 17? So 17 is, let me make sure I get this right. Yeah, okay. 17 is just another indefinite integral x to the 5th over 4, oh, no, I need to make sure. Don't mix them here. Over 1 minus x to the 6th raised to the 7th power dx. Whoa, okay. What does this problem look like we're going to be using?
Quotient.
Ooh, quotient rule is if I was taking the derivative,
Yeah.
but I'm doing an integral. It means I need to find the antiderivative. So what am I doing with this one?
Would you be converting it to be all? I forget anywhere. Like not as a fraction anymore, but with like negative.
You could. I can move that up into the numerator. In fact, we'll probably want to eventually. So we could do that, but I don't have to do that right now, if that helps at all. But sure, we're going to want to do it eventually, so let's do it. But that's not what I was fishing for. What am I fishing for, Darius? Yeah, I'm going to use a u substitution. Right. I have an inside function here. So let's choose, let's use u as my inside function. And let's try and convert this integral completely in terms of u now instead of x.
Where did x to the 5th?
Oh, yeah, sorry. X to the 5th. That's still x to the 5th. Okay. So if I'm going to do this, then what else do I need to convert in terms of u?
X to the 5th would not outside.
Yeah, we're gonna wait on the x to the 5th because we're gonna see that x to the 5th ends up being pretty important for us. Dx, right? I can't keep it in terms of x if I'm gonna change things in terms of u. So I need dx. How do I get dx? Just by integrating, by just finding the derivative of my substitution here. So I get du is equal to negative 6x to the 5th. Which of course means, times dx. So I can just find du and dx by using that idea of differentials and then solve for dx. And so remember, we had this conversation quite a bit in class when we learned this. Is this substitution going to work? Is this substitution going to work? Is this substitution going to work? Yeah, it is. Because this x to the 5th right here is going to cancel with that x to the 5th. Right? That's why that x to the 5th is so important to this. We need that there in order to cancel out with my differential x to the 5th. So what am I left with when I'm done? I'm left with this integral of u to the negative 7th times du over negative 6. And what can I do with that negative 6? It's a constant, so I can just pull it completely in front of my integral. But now that I've got this is where it's nice that we already moved the fraction up to the numerator. Because now that's just a power function. And I can use my my power rule for integration on that. So I get 1 over negative 6 times u to the negative 6th over negative 6. And we're done, right? Oh, yeah, I can't forget. This was a substitution. So I need to put my original function back in for u, right? What was u? U was 1 minus x to the 6th. Now I'm done. I'm not done. What did I forget? Plus C. Another indefinite integral. Remember, you will get the problem wrong on your test. If you do all of this wonderful work and it's all wonderful and great, but you forget to put that plus C, you'll get the whole problem wrong. And that's where, like, I will probably go adjust your grade, but still, you will miss points if you don't have that plus C on there. Okay? So make sure to include that if you're working with an indefinite integral like this. And then just, we always could go ahead and just move that back down to the denominator if we wanted to, since it's a negative exponent. But you don't have to. You don't have to do that for your test. Okay. Any questions on this one? Okay. I'll move on then. Number 18. Let's see. Okay. This is, let me make sure I know which one I'm talking about here. Oh yeah, this is your, so now we're on to chapter 5, because this is getting into how do we use integrals. And so this is my consumer surplus demand, or producer surplus problem. So first, it gives me a consumer demand equation. So that's my consumer demand equation. And then it gives me my supplier demand equation. Okay. And if you remember, these questions all kind of work the same. First, it wants you to find the equilibrium point, and then it wants you to find your consumer surplus and your supplier surplus. So let's start with that first part. How do I find the equilibrium point? Set them equal to each other, right? Very nice. So I'm going to do d of x equals s of x. So x minus 4 squared equals x squared plus 2x plus 6. Well, the only way I'm going to be able to solve this is if I expand that x minus 4 squared. So that's going to give me x squared minus 8x plus 16. Very nice. Now what? Now what happens? Yeah, so I can start moving the x's all onto one side, right? From here, right, I'm just moving things around. Tell me about the x squareds. Yeah, if I subtract x squared to move it over to the other side, they just end up canceling out on both sides. Very nice. And so then I'll go ahead and I'll add 8x just to get rid of the negatives. And then everything that's not an x, let's move to the other side. So I'm going to subtract 6. And that leaves me with 10 equals 10x. Oh, that's nice. There's my equilibrium point. So I want to produce one product. Very nice. Okay, so now that we have the equilibrium point, now I can calculate consumer surplus and producer surplus. Remember, consumer surplus, the actual revenue is going to be, or the actual amount that customers pay is going to be less than what they're willing to pay. And so the area under the curve is going to be the bigger value. So I'm going to do the area under the curve from where do I start? You always start at the same place. 0. I'm always going to start at 0. 0 to the equilibrium point. Right. So in our case, 0 to 1. So I'm going 0 to the equilibrium point. 0 to 1, what am I integrating? This is consumer.
Consumer demand.
Yeah, this is consumer surplus. So I'm going to integrate the consumer demand equation. So x minus 4 squared dx. Okay? And then I subtract the actual amount that the consumer pays, which is how do I calculate the actual amount? This piece follows that kind of general rule for revenue of just price times quantity. So what's my quantity? 1. How do I figure out price? Let's come back up here. Because the whole idea of that equilibrium point is this is the point where the amount of products and the price that I sell it at agree, where it's going to be the same for both of these functions. So the work we did showed that, hey, we should really be selling one product. What price am I going to sell that one product at? How do I figure that out?
Plug in one for your equation.
Where? Which equation?
Either one.
Either one, because that's the idea, is this equilibrium point, they're crossing at that point anyway, so it's going to be the same for both equations. So you'll notice that if I plug it into my consumer demand equation, I get 1 minus 4 squared, which is negative 3 squared, which is 9. If I plug it into my supplier demand equation, I get 1 squared plus, oh goodness, plus 2 times 1 plus 6. And I'm left with 1 plus 2 plus 6, which is 9. So you get the same thing either way. And that's the price that I'm selling at. So to get that price, you just plug it into either of your two equations to see what you get. So that tells me I'm going to be selling my product. I'm going to be selling one product at a price of $9. So 1 times 9. That's my actual revenue. That's the amount that the customer actually pays. And now I can work through this. Okay. So I have this integral. A couple of different ways I could go about this. I could use a u substitution for x minus 4. It's actually not too bad at all. But I would need to change my bounds because I have an indefinite integral. Or I could just multiply it out, which since we've already multiplied it out, we might as well just do it that way. And 1 times 9, of course, is just 9. So then that gives me my antiderivative of x cubed over 3 minus 8x squared over 2, which just simplifies to 4, of course, plus 16x, evaluated from 0 to 1, minus 9. If I plug 1 in, I get 1/3 minus 4 plus 16. If I plug 0 in, I get 0. Yeah. So, and then minus 9, which is 3 1/3, 3.3 repeated. And there's my consumer surplus. Very nice. Questions? Questions about consumer surplus? Producer surplus. Very similar, except what's the differences?
We're using the consumer surplus equation.
Right, now I'm going to switch which equation I use. So now I'm going to be integrating my supplier demand function instead of my consumer demand function. What else? How else is this going to change? What comes first in the producer surplus?
Isn't the integration the second?
Yeah.
Minus the integration.
Right. With producer surplus, it's the opposite, where your integration comes second. The area under the curve is going to be the smaller value, and the actual amount is going to be the bigger value. So So with producer surplus, I'm going to start with that actual amount, which is the same because we're using that equilibrium point. So I'm still selling one thing at a price of $9, and then I'm just going to subtract the integral from 0 to 1 of x squared plus 2x plus 6. Notice my bounds are also the same because I'm still starting at 0 and I'm still going to that equilibrium point. Okay. So what does that give me? Let's see. That gives me 9 minus this integral. So my antiderivative is x cubed over 3 plus 2x squared over 2 plus 6x evaluated from 0 to 1. And I get 9 minus 1/3 plus 1 plus 6. Once again, what happens when I plug in 0? That's what's nice about polynomials is if you ever have a bound of 0, you're just going to get 0 when you plug 0 in. Nice. And what does that give me? That gives me, let's see, 9 minus 7 is 2 minus another 1/3, so that gives me 1 2/3, or 1.6 repeated. And there's my producer surplus. Very nice. I guess you can't plug it in with the repeated decimals. No, well, let's see. I'm not sure how the input works there. So right, this is also just 3 and 1/3.
In the instance where it's repeating, I think they would have you either put it as a fraction or have you round it.
Yeah. So 3 1/3 and 1 2/3. Okay. Any questions about producer or consumer surplus? Any of that kind of stuff? Okay, and remember the formulas for both of those will also be on your formula sheet. So, okay, number 19. This is my grandchild problem, which we went through this one in class, but you've got grandparents that just had a grandchild and they want to set up a nice fund for that grandkid, where they want to have, I think, for my problem, they want to have $280,000 in the account after 18 years. Okay. It also gives me a rate. Part A is asking the same type of question that we just covered back in, what was it? Number 13. It's the same problem as number 13 because it's asking the same question. How much do I need to invest right now in order to have this much in this many years? So it's the same exact question, so I can use the same process. Okay. Oop, come on. No. Okay. So I can use that present value formula where I say, okay, my present value is going to equal, and then I can use that future value as my starting point, and then use a negative rate so that I move backwards. E to the negative 0.056 times 18. Everybody okay with that? Throw that into your calculator, and you get 102,185.48. Okay, questions so far? You okay with that? So now I'm at present value. Okay, so where does this turn into chapter 5? Well, in chapter 5, in 5.2, we learned about accumulated, or a revenue stream, right? Accumulated future value or accumulated present value if you're consistently contributing towards a certain account or fund. And so the next question is, okay, well, instead of investing $102,000 all at one time, how much would they need to contribute each year in order to end up with the same amount? Okay. So from here, there's a couple different ways I can go about it. Remember, we had a formula for future value of an accumulated value stream, and that one is A equals R of T, or over K, e to the KT minus 1. I wrote it like that, but remember, what are we assuming about capital R? In order to have this nice, simple formula for us to use, what did we assume about that income stream? Constant. So it says in here that it's a function. It's not a function. It's constant. It's always going to be the same amount. Okay. So that's my future value equation. But my present value equation was very similar. We used B for present value. R over K, and remember K in this case is my interest rate. So I really should change that up here. We're going to use K for the interest rate. 1 minus e to the negative KT. So that's present value. Future value and present value. And there's actually a couple different ways I can go about this. I can use either of these formulas. If I use the first one, what value am I solving for?
Future value.
No, I know the future value.
You're solving for the consistent.
Yeah, I'm solving for that income stream. I'm solving for capital R. So I'm solving for capital R. Put a little question mark there. That's what I'm solving for. And so what do I plug in for A? 280,000, because it represents my future value, what I want in the future. Okay, so that's one way I could set this up. I could set it up as, okay, 280,000 is equal to R over 0.056, e to the 0.056 times 18 minus 1, right? My rate is that 5.6%, and then time is 18 years. Okay. So I can set it up that way. Or I could also use the second equation. What am I solving for in the second equation?
I'm solving for also.
Yeah, same thing. I'm still solving for R. The difference here is, do I know what the present value is? Yeah, that's what I did in part A. The present value is just that 102,000. So I could also set it up like this. 102,185.48 is equal to R over 0.056, 1 minus e to the negative 0.056 times 18. I will say this conceptually this works, but the problem with doing it this way is I did round to find that present value, and therefore your answer is going to be a little bit off if you use this second method. But if I do it using that first method, you should just get R is equal to $9,010.90. It means they have to contribute $9,000 every year to this fund. That seems a little too generous for this grandchild. I'm sorry. That's not worth it. Okay. Next. So this one, number 20, is depletion of a natural resource. I kind of mentioned in class how, hey, we can actually use this accumulated income stream formula for depletion of natural resources, but we didn't actually ever go through an example. So this is where we get to go through an example of that. So this is number 20. Oh my goodness, I should just start over. It's number 20. And it says, let's see. So in the year 2006, let me see if I can kind of keep track of this with a table. In the year 2006, let's see, the world reserves of natural gas were 8,015 trillion cubic feet. So that's the reserves of natural gas. So I'm going to just use an A for amount. Okay. And it does mention that 2006 is going to be my baseline, so that t value is just going to be represented by 0. So that represents t equals 0. Okay. But then it tells me that the consumption of natural gas was approximately, so the consumption is equal to 110.1, let's see, trillion cubic feet per year. Per year. So that's a rate. That's how it's changing. Okay. And then the last thing it tells me is this is growing at a rate of 3.1% each year. So the rate at which we're consuming the natural resource is growing at 3.1%. Okay? Now you might think, what the heck? How is this related to what am I trying to say? How is this related to a consistent revenue stream or with accumulated value? How is this related to accumulated value? Well, it turns out the way this is related is because you're consuming a certain amount each year, and that's growing at an exponential rate, you can use your accumulated value formula to actually calculate this. So, your total consumption, heck. I guess if we want to, let's see, oh man. Oh, okay, so it's asking, let me just make sure I get my bearings here. It's asking how many years will it take before the world reserves are gone? So what are we solving for?
A equals 0.
A equals 0. Future value is equal to 0, right? So that's one way you can think about it. What are we solving for, though? So that means we know what the future value is.
We're solving the price.
We're solving for t. So we're solving for what year will it be when my total amount is 0. Okay, so that means I technically know a future value, but a future value of 0, I'm trying to think what would happen if I tried to do that. What the heck? What the heck? Okay, this is throwing me off. And it's probably because we didn't do one of these when we actually did this in class, when we covered this in class. It might be a good time to mention there is not a consumption problem on the test. So, but I did want to put it on there, on the review, just so we understand that we can use this for stuff that's not just finances. But let's see. In that same year, right? So, okay. So I guess the idea behind this is we want to say, okay, my yearly amount that I consume is 110.1. But this is growing, let's see, by 0.031. So that's my rate.
Times t.
But I'm using a future value here. I'm going to use the future value formula. So 0.031 times capital T. Once again, I'm solving for that T. I don't know that T yet. But I'm using a future value formula because I'm looking at, okay, when will this consumption total 8,015. Because as soon as that total consumption matches what I currently have, then we're done. Then we've consumed everything. And so that's how I would set up this problem. So I'm using a future value because I'm looking at when my consumption will end up being 8,015 to match what my actual amount is, the amount that I have available. Okay. And so then I would just solve this, and I think, how do I solve something when t is in the exponent?
Starting with it, you would divide by.
Yeah, there's some stuff I can do first, right? I can go ahead and divide these, and then divide that over,
Then you would turn it into a natural.
and then I would use a natural log to get rid of this e. Right. So just a little reminder there. Use a natural log to get rid of that e. Whew. Okay. Got that one over with. Whew. Okay. Awesome. So 21. So another accumulated present value one, but this one is slightly different because this is a perpetual money flow. So perpetual continuous money flow. What does that word perpetual mean? Yes, it's continuous in the fact that it's happening every year, but how else do you mean continue? What does that word perpetual mean? Let's see, what does it tell me? It tells me that I'm perpetually adding, sorry, I don't put parentheses here. I'm perpetually adding $3,400. Okay? It tells me the interest rate. Yeah, perpetual means there's no set endpoint. I'm not saying I'm only going to do this for 5 years or I'm only going to do this for 10 years. This is saying I'm just going to do this forever, as long as I can. No set endpoint. And if you remember, this is related to improper integrals. Can I calculate future value? Can't calculate future value. Not if there's no set endpoint, right? Because theoretically, then your future value is an infinite amount of money. So I can't calculate future value, but I can calculate present value, which is exactly what this problem is asking. It asks you, find the accumulated present value of an investment if there's a perpetual money flow. Okay, and if you remember, this problem broke down really, really easily to just a simple R over K. That's all it ended up being. The reason why is because if you think about the rest of the formula, you get this 1 minus e to the negative r, or negative kt. But if you're letting t get infinitely large, this is the k function, so that just goes to 0. So you end up with this times 1. So in this case, in our case here, we get present value is equal to this 3,400 divided by 0.06, which is
56,000.
56,000, and then you've got some repeated sixes, yeah. So that's my present value. Awesome. Okay. Moving along. 22. Oh, no, that was 22. No, I'm off again. No. I'm looking at the wrong one. Sorry. 22 is now we get into multivariable functions. No, we have one more. That's right. This is our probability density function problem. I have to remember that I added
So are
some.
we doing 27 problems in total for review?
Yeah. There's 27 problems on the review, and we'll go through all of them. Okay, so number 27 says, hey, we've got this probability density function. It labels it as f of x, but if you remember, usually with probability density functions, we use capital P. But we're talking about the same thing here. Okay. So a dart is thrown at a number line in such a way that it always lands in the interval 0 to 10. So there's my bounds of this this probability density function. I'm restricted to between 0 and 10. What is the probability that the dart lands between 9 and 10? Somewhere between 9 and 10. Well, the whole idea of 5.4 is if you have a probability density function, you can use integration to solve for probabilities. So, how am I going to set up my integral? How do I set up my integral here? It's for sure going to be an integral. So I'll put my little integral symbol. Bounds? What is bounds?
9,
Hmm?
would be 9 and 10.
Yeah, 9 and 10. That specific area that we're looking at. So your bounds are that specific region that you're concerned about. Right? It's 9 and 10. What am I integrating?
You want
Yeah, the probability density function itself. Right? That's what I'm integrating. Okay. Remember, what makes it a probability density function? If I were to integrate this from 0 to 10, what would I get?
you get, wouldn't it be like 100%?
Yeah, you get 1, because there's a 100% chance that your value will be between 0 and 10, because that's my set range of values. Okay? But for this one, right, I'm looking at this specific region from 9 to 10, and I can go ahead and integrate this. So I can pull that 150 out. What's the antiderivative of x? X squared over 2. So I get 1 over 100 x squared, evaluated from 9 to 10, which is, oh nice, 10 squared over 100 is 1, minus 9 squared over 100 is 81 over 100. So I get 19 over 100. That actually is really nice. If it's a 19 over 100, what percentage is that? Yeah, that's just 19%. Nice. Good. So there's a 19% chance that it'll end up in between 9 and 10. Notice how this isn't just uniform distribution, right? That's a higher probability, even though this is only 1/10 of your range. And that's because if you have a linear probability distribution like this, this means that it gets more likely the bigger the number. Okay, sounds good. So there's my probability problem. Okay, moving on. 23. Now we get into multivariable functions. So the rest are all related to chapter 6. And this one's just a nice simple one of, okay, here's my function, and it's a function of 3 different variables defined as 5x minus 8y squared plus 9z cubed minus 6. And all this one's asking for is, hey, what's f of 6, negative 4, 1? Well, what does that want? What does it ask me to do? How do I evaluate this?
You don't put in the value.
Yeah, plug in the values. Plug 6, 4. Where does 6 go? Six is your x, negative 4 is your y, and 1 is your z. So 5, I'm going to plug 6 in for x, negative 4 in for y, and 1 in for z. And I'm left with 30 minus 128 plus 9 minus 6, which is negative 95. Oh, nice easy one. Nice easy one. Okay, 24. We're going to keep on with this idea of multivariable functions. So next I have a function in terms of two variables equal to 8 times the square root of 7 plus x squared minus y. And this is my domain question. What's the domain of this function? Can I just plug in any x, y that I want? No, why not?
Because it has to be, it can't be square root of 0.
Because I have a square root. I can actually have square root of 0, negative, right? I just don't want a square root of a negative. So that's why domain is actually relevant in this problem. What's my domain? Because I can't just plug in any numbers I want. I have to make sure that this thing under the square root stays positive. So remember, I can just write that using an inequality. 7 plus x squared minus y has to be what?
It's equal to
Greater than
0.
or equal to 0. Greater than or equal to 0. Now what? In order to, what's the word?
Would you set it down to one variable equal to the other? So like
Yeah.
Negative y, basically.
Yeah, there's not much more I can do here besides just solve for a variable. Solve for a variable. So, and the easiest one to solve for is y. So if I just add y to both sides, I get 7 plus x squared is greater than or equal to y. And I can turn that around and say, okay, this function will exist as long as y is less than or equal to x squared plus 7. So as long as that's true, the function will be defined. This function will exist. Okay. That's my domain. And the technical way to let's see if I can see this one. Because the technical way to write this is they use the little squiggly lines, because this is just saying, okay, you can pick any x, y such that y is less than or equal to x squared plus 7. That's kind of what that notation actually means. Okay. Very nice. Very nice. Okay. 25. How are we doing on time? We got 10 minutes left? Okay. 25. So this is where we get into derivatives, partial derivatives. So here's my function. F of x, y is equal to the square root of x squared plus y squared. And this is just asking me, okay, what's my partial derivatives for each of these? What's my partial derivative in terms of x? Remember, the idea behind partial derivatives is you take the derivative like normal, but you treat the other variable as constant, as if it's just a constant value. So here, since I have x squared plus something inside of a square root, I still need chain rule, right? So I get 1/2 x squared plus y squared raised to the negative 1/2. That's what happens after I use chain rule. But then I have to multiply by the derivative of the inside function. What's the derivative of x squared plus y squared? Just 2x. Because if I'm treating y squared as a constant, then the derivative of y squared just goes to 0, right? That's not changing as x changes. Well, tell me about f the partial in terms of y. It's the same exact thing, except,
You're using times 2y.
yeah, except you just multiply by 2y. And these actually simplify pretty nicely. This just simplifies to x over the square root of x squared plus y squared. And this one simplifies to y over the square root of x squared plus y squared. And then it also asks you for f, like the partial derivative of x of 3, negative 5. And what is that telling you to do? Yeah. Just plug those values in for x and y. Plug 3 in for x, plug negative 5 in for y into your partial derivative. So this would be 3 over the square root of 9 plus 25. So 3 over the square root of 34. Okay, we're going to go ahead and move on then to 26. And this one will look familiar. This is the units of labor and units of capital problem. So you've got a sports company whose production can be modeled as this. Oh wait, I got to make sure and use my numbers. Yeah, there it is. X to the 4/5, y to the 1/5, where x is units of labor and y is units of capital. Okay. And so this is just having you find your partial derivatives, plug in your value, and then what is that partial derivative going to actually represent? So let me just run through it pretty quick. My partial derivative in terms of x is I'm going to treat y as a constant, and I'm going to treat 2,000 as a constant, which means they both just stay there, and I'm just taking the derivative of the x to the 4/5. And so I get 2,000 times 4/5, which is 1,600, y to the 1/5 times x to the, and when I use that power rule on this for the derivative, 4/5 minus 1 gives me x to the negative 1/5. Okay. Everybody okay with 1,600? That's just 2,000 times, when I bring that exponent down for x to the 4/5, 2,000 times 4/5 gives me 1,600. Okay, and then it asks me for p sub x of 25 and 1056. So that just means I'm plugging that in for x and y. So I get 3,383. Now the reason I'm skipping ahead so fast is because I really want to talk about what does this mean? What does that actually mean? First of all, we need to recognize that this number is a rate. Why is it a rate?
It's using the derivative.
Because it's a derivative. We used a derivative to find it. So this is a rate. This is, I'm going to produce 3,383 more units per what? What did I change? Units of labor. This was the partial in terms of x. So what am I changing? I'm changing the units of labor. So units of, let's see, I'm trying to think. So we talked about how units of labor can be think about as workers. So this is units per additional worker that you hire. But another thing to keep in mind, though, is this is at a specific point in your kind of production process.
When hiring one more worker, when hiring 26.
Right. We already have 25 workers, and this is what's going to happen if we hire a 26th worker. So what are we assuming? We're assuming we're already at 25 workers when we have 25 workers. And what else are we assuming? What does that 1056 have to do with things?
The amount of product.
Well, I mean, I'll just keep it as units of capital, but But the idea here is we have 25 workers. We're adding a 26th worker. This is how much it's going to change. How are we changing the units of capital? How are we changing the units of capital? How did we change y? When we took this partial in terms of x, what are we assuming about y?
Y was constant.
Y is constant. So the other big thing here is we also have to recognize that with this rate, we're assuming that the units of capital is staying fixed. It's staying constant. We're not changing the units of capital. We're only potentially adding a worker. And that's what this rate represents. If I keep the units of capital fixed at 1,056 and I add one more worker, this is how many more units we're going to be able to produce. Everybody okay with that? Makes sense? Okay. Sounds good. Okay. We got 2 minutes to run through number 28. Okay. Whew. I don't know if we're going to be able to finish this.
28.
Sorry, 27. It's because I deleted, since I made this, I've deleted one. So now you only have 27. Number 27. So a company produces two types of solar panels. X thousand of type A and Y thousand of type B. So X is for type A, Y is for type B. And the revenue and cost equations are follows. So it gives you a revenue and a cost. And then it wants me to maximize the profit. Maximize profit. Well, if I want to maximize profit, I need a profit equation. But in this case, it's in terms of two different variables, X and Y. Profit is, how do I calculate profit? Revenue minus cost. So I'm going to do my revenue equation minus my cost function. So revenue is 6x plus 4y minus my cost function, so minus x squared. Let's see, I'll put a parentheses there. Minus 3xy plus 7y squared plus 7x minus 26y minus 2. Okay. Simplify all this, and I get negative x squared plus 3, plus 3xy minus 7y squared minus x plus 30y plus 2. So that's when I combine all my like terms. That's my profit function. It's my profit function. If I want to maximize profit, now what do?
You would want to have the derivative be equal to 0,
Right, because I'm finding those critical points, right? I want to find critical points. I want to find where my function has a mountain or a valley, right? In this case, maximizing profit, we want a mountain. We're looking for a local maximum. So I want to find those critical points where the derivative is 0. But in this case, I have to do that twice, right? I have to find both partial derivatives and set them equal to 0. So P sub x is equal to negative 2x plus 3y minus 1. You'll have to check my work later. We're out of time. And P sub y is equal to 3x minus 14y plus 30. What do I do with both of those? Set it equal to 0. I want both to be equal to 0. Okay? And then you're looking for your critical point. Set them both equal to 0. And because you have two unknowns and two equations, remember, you're going to have to use a little bit of substitution here, right? So for this first one, you can solve for it and get, oh, hello. Where'd you go? You can, oh my goodness. Very nice. You can solve for it and get x equals 3y minus 1 over 2. Right? That's just adding 2x to the other side and then dividing by 2. And then you can plug that into your other function, right, and get 3 times 3y minus 1 over 2 minus 14y plus 30 equals 0. And you can solve and you'll get like y equals 3. And so there's your optimal production in order to maximize your profit. Okay. Whew. Went a little fast there at the end, but we got it all done. So I will also post this on Canvas. You can go back as you're working through the review. You can come back and look at some of these problems just to kind of refresh yourself on it. And then don't forget to be here 1 o'clock on Wednesday down in the basement of this building. Basement of the snow building is where the tutoring center is.
Wednesday wasn't Monday?
Not Monday, Wednesday. Yeah, I changed it because I had it wrong on the syllabus. I had it wrong. And so when I went back and looked, we're actually scheduled for Wednesday.
What is the type of calculator allowed that is?
Scientific calculator. So I will have some there in the tutoring center. I'll have a limited number of them. I'll have like 8, maybe 7 or 8.
I really want to repeat what happened last
right.
time with my
So if you have one, bring one. Otherwise, you might be able to borrow one just while we're down there. So
yeah, because I'm the ones that are in the testing